algorithm approach. So in previous video, we have seen how dynamic programming works, how gradient method works. Backtracking is also used like dynamic programming and gradient method for solving the optimization problems. Okay, so backtracking is basically approach for solving constraint satisfaction problems without trying all possibilities. So simply we can say that backtracking solves problem recursively by trying to build a solution incrementally one piece at a time and removing those solutions that fail to satisfy the constraints of a problem at any point of time. Okay, so we'll take a simple example. Consider a situation that you have three boxes in front of you and only one box, one of them has a gold coin. But you don't know which box is having gold coin. So in order to get a gold coin, what you will do? You will first check the first box. If it does not contain coin, you will choose the another one and check the third one. So until you find the coin, you will repeat this process again and again. Right. So this is how backtracking solves all sub problems one by one in order to reach the best possible solution. So of course, backtracking it uses recursive approach. It uses recursive calling to find the solution by building a solution step by step. Okay, so we can say that backtracking is used to find all possible combination to solve an optimization problem. So you can say if I want to apply a backtracking approach for solving a particular problem, what it will do? It will check first whether the solution is obtained or not. If the solution is obtained, then there is no need to apply backtracking. If the solution is not obtained, then what it should do? It will again backtrack and it will search for another solution. So this process it will repeat till the solution is found or all the paths have been discovered. So here in this diagram, we are going to construct a tree to understand in detail way how backtracking works. Okay, so backtracking is actually a systematic way of trying out different sequences of decisions until we find one that works. So in the figure that we are going to construct, each non-leaf node in a tree is a parent of one or more other nodes. Each node in a tree other than root has exactly one parent. We will see it. So for every tree there is a unique root. Every tree it starts with root, right? So start is our root here. Now what I am going to do, I am going to discover the solution, the correct solution for my problem by using backtracking. So if I have started, I discovered the node. From that node I will check whether any particular solution is available or not. If it is not available, it will go ahead till a dead end for that particular path has been recovered. Now dead end is the last end. It is the leaf node. So what it should do? It will backtrack. You can see here. You can see here it is backtracking to a particular node from where it has been started. Again, for this node, it will check a possible path. If it is a dead end, what it should do? It will go for the backtracking. Again, the same thing it will repeat. It will backtrack. Again, a new path will be discovered. It will check. It will check for dead end. If it is a dead end, the backtracking has to be done here. So again, it is backtracking. One more possible path it is trying to discover. You can see this is again a dead end. No solution is found. It is trying for a new path. Again, it is backtracking. Again, it is backtracking to the starting point. Now, it is again trying to find out a new path. And you can see here that the node or the solution that we are going to find has been discovered. So the simple thing here is that in this diagram what we are doing here, the tree is composed of one root node. We have already discussed that the start is our root node. Start node is there. Internal nodes are there. Internal nodes are nodes those are having child, and leaf nodes are there. The leaf nodes are our dead ends. So if any leaf node or any dead end is encountered, what we are doing, we are backtracking for another path because we didn't get our solution. We have to backtrack it. And major thing is that backtracking can understand like searching a tree for a particular goal leaf node, right? So you'll see a simple code at how nodes can be explored. So keeping the diagram, keeping the tree that we have constructed in mind, we will see how this particular code can work. So if n is a goal node, what is n? N is the node. N can be goal node. Goal node is the node that we are searching for, where our solution lies. So if n is goal node, it will return success. If n is a leaf node are the dead nodes that we have already discussed. It will return failure. Now see where the backtracking can be used. For every child C of n. Now here n is internal node. It is non-leaf node, means it is having certain children. Right. So for every of the node, for every of the C of n, it is going to explore C. And if C is successful, then it will return success. Otherwise, it will return failure. Okay, now constraints, right? So, how will you determine if a problem can be solved by using backtracking? So, for that, we need to understand what constraint satisfaction problem is. A problem which being solved by applying certain constraints is called as constraint satisfaction problem, right? So if I want to know that whether a particular problem I can solve it by using backtracking or not, what I have to do, I have to check every constraint satisfaction problem which has a clear and well defined constraints on any objective function that incrementally builds candidate to the solution and backtracks a candidate as soon as it determines that the candidate cannot be possibly completed. So here we can use backtracking. So the fact is that most of the optimization problems can be solved by using dynamic programming or greedy approach. So where they are taking log time, linear time in terms of input size. If we are comparing backtracking with those algorithm approaches, backtracking algorithms are generally exponential in both time and space, but still there are few problems which can be solved by using only backtracking. So we have to use backtracking over there. So constraints, when I'm talking about constraints in backtracking, the constraints are of two types. One is explicit constraint, another is implicit constraint. What are the explicit and implicit constraint? Explicit constraint is ruled which restrict each vector element to be chosen from the given set. And implicit constraint is rules which determine which each of the tuples in the solution space actually satisfy the criteria function. So we have to understand here that backtracking is used for solving certain optimization problem, but it is applicable only when certain constraints are there. Now we will see with an example how the constraint can be applied. We will take an example of Sudoku. Everyone of us aware with the Sudoku, but just for the people who don't know, we'll see what exactly Sudoku is. So the Sudoku is a basically puzzle. The objective of Sudoku puzzle is to fill 9 by 9 grids with a digit so that each column, each row and each of the 9 3 by 3 subgrids that compose the grid, which we can also call as boxes. You can see in the diagram on the screen, contains all the digits from 1 to 9. Okay, a Sudoku puzzle is partially completed grid. Now, as I told you, every backtracking algorithm has certain constraint, and constraint for solving this Sudoku problem with the help of backtracking is that every number, every number appears once in each horizontal line, in each vertical line, and in each square. So here you can see in the diagram, each time a path is tested, if the solution is not found, another possible path is checked, and so on until two things. Either the solution is found or all paths have been tested. So you can see here in this diagram, the red cell here encounters when the solution is not found. If the solution is not found, then what we have to do, we have to backtrack it for another possible solution. Okay, so like we can take one more example of maze also. Okay, so the typical scenario where a backtracking algorithm is when you try to find your way out in a maze. Every time you reach a dead end, you backtrack to try another path until you find the exit or all paths have been explored. So you can take example of Sudoku, you can take example of puzzle, you can take example of maze. All these problems are solved only with the help of backtracking. So, though backtracking is exponential in terms of time and space, certain problems can be solved by using backtracking only. So, these are the references that I have referred for making this video. In next video, we will discuss about n-quince problem. Thank you for listening to me. Thank you.